We're going to be looking at the idea of a limit, and we're going to kind of survey most of the limit topics. There are some properties of a limit that we'll be taking down as notes in tomorrow's class. But aside from that, we're going to cover everything else. So the formal definition of limit says that if we've got a function that's defined on an open interval, so just like this function on the right here, we've got a line, right? It's defined on that interval. It contains a point C, but not necessarily defined at C. Let L be a real number. Then the limit as x approaches C is equal to L, and we have an epsilon and delta both bigger than 0, such that we've got the absolute value of x minus c is less than delta, and the absolute value of f of x minus L is less than epsilon. So basically what we're saying is, as we shrink our distance here, as that gets smaller, it corresponds to an epsilon getting smaller on this side. So we're going to be investigating the relationship between that delta and that epsilon. For instance, my delta down here could be decreasing at a rate of 1, while the epsilon decreases faster, like at a rate of 3. So we're figuring out how those two distances are related. I shouldn't have said rate, I should have said distance. So we're going to look at this graph on the right and do a proof of its limit. We have a statement here. The limit as x approaches 2 if 3x minus 2 is 4. And we're going to set up using our c, f of x, and L from that limit statement to set up f of x minus L is less than epsilon. And then we're going to strive to make it match the x minus c is less than delta. Once we've done that, we're going to choose a delta equal to that epsilon expression. So you'll see exactly what I'm talking about in just a moment. So I've got my f of x, 3x minus 2, minus my L, which is 4, less than epsilon. And the goal, what we're going to be trying to make it match, is x minus my c, which is 2, less than delta. So we combine our like terms. We've got 3x minus 6, less than epsilon. We can pull out a common factor of 3. Got 3 times x minus 2, less than epsilon. You'll notice we're getting close to what we want, that x minus 2. So if we divide both sides by 3, we're going to have x minus 2 is less than epsilon over 3. So we're going to choose to have our delta equal to epsilon over 3. So we say choose delta equal to epsilon 3, and then we've proven the limit. So we can put a little box that says we've proven it. All right, now we've got some properties we're going to talk about. So let me just actually erase this. So we have cases where the limit exists and cases where it doesn't. So for the limit to exist overall, that means for the limit as x approaches c of f of x exists if the limit from the left is equal to the limit from the right. So in my example, I used pink and yellow, and that's what I'm going to use throughout class today. So I'll use pink and yellow when I'm writing out the notation as well. So we're going to look at as x approaches c from the left of f of x. And we're checking to make sure that's equal to the limit from the right. The little plus and minus in the air is what symbolizes to us the direction from which we're coming in. So we've got this example over here. Let me zoom in. And of course, it's not going to let me move the screen. So for this example, we're trying to figure out, well, what's the limit as x approaches 2 of f of x? Does it exist? And if so, what is it? So then we have to consider the left-hand limit. So we're looking at 2 from the left. So that's this pink arrow I have here. As we get closer to x equals 2, what does my y get closer to? And that is 5. Then we look at our yellow from the right, and we say, well, what does that get closer to as I come in from the right? And you'll notice they're both getting closer to the same value. of 5. So since these are equal, we say the limit as x approaches 2 of f of x exists and is equal to 5. So that's a limit existence theorem with a concrete example. Now let's talk about cases where the limit doesn't exist or it fails to exist. So does not exist, this part here, we're going to abbreviate DNE going forward, right? But our limit doesn't exist if that left and right limit aren't equal, right? If our limit approaches positive or negative infinity, so think about the limit as we go towards a vertical asymptote, and if it oscillates. So we've got 3 cases, and we've got an example for each of those 3 down below. So for the first case, I've got a function here that from the left approaches 2, and from the right approaches 4, so the limit overall does not exist. My second case, I'm looking at a vertical asymptote. So from the left, I approach positive infinity. From the right, I approach positive infinity. Both of those are infinite, so they don't exist. Therefore, my limit overall doesn't exist. When I have something that's oscillating like crazy, so this would be 3, it's hard to determine what my limit is. So we say it does not exist because it's just jumping between values. We can't tell what it is, so it does not exist. So those are 3 cases. So I'll zoom out, you can see all 3. And pause the video if you need some time to write it down. Let's look at some concrete examples right now. Come on. All right. So if we look at as x approaches -4, let's do from the left. Remember that minus in the arrow is telling me from the left. So x at -4, this is -4. So from the left, we approach, and this, in case you can't read it, is at -6. And then we have the limit as x approaches from the right. That with the little plus in the air tells us it's -4 from the right. And from the right, as we get closer to that -4 of our x, we approach instead about -2.5. These two are not equal, so the limit overall does not exist. Let's check out -3 now. So -3 is this guy right here. So we're going to do both sides again. So limit as x approaches -3 from the left with the little negative in the air, telling us that means from the left. So from the left, we approach 0. And then we're thinking about, okay, what about from the right? So remember, we're going to put a little plus in the air to symbolize from the right. And from the right, we also approach a y value of 0. These two guys are equal, so my limit overall exists and is equal to 0. Now we have from the right, as we go towards 4. So from the right, as we go towards our x of 4, we are going down forever, right? Down, down, down. So that's infinity, or it does not exist. Then we've got the squeeze theorem, which I don't want you to write down. But basically, this is if we have a function f that's a hot mess, we can make up an equation g that's above that function and h that comes up from below, and find the limits of those two guys, and that'll give us the limit for f. So let's look at an example. Right here we've got the function x squared cosine of 1 over x, and that's a really messy function. It's our middle one there in black. So what we do is we come up with one from above and below that intersect at that point. And we've got x squared as our top one and negative x squared as our bottom. So we look at those limits instead when we're trying to figure out the limit as x approaches 0 for f of x. We're going to look at it for each of those. So x approaches 0 for x squared. Direct substitution, which we're going to do in just a moment. We substitute in that value, we get 0. And as we do it for the negative x squared, we also get 0. So we then know that our limit for f of x is 0, because the one that's above it and the one that's below it both give us 0. All right, our three methods for evaluating limits are going to be numerical, which means we're using a table of values on either side of C to figure out what that limit L is. Analytic or algebraic, we're going to try direct substitution first, but then when that fails, we'll be simplifying or rewriting our equation and subbing C into our simplified version to get our limit. This is where we're using skills like factoring and rationalizing the denominator or the numerator, those algebraic skills. And then graphical is what we just did, where we're working with a graph to find the limit. We're always going to try direct substitution first, aka plugging into our equation. So for this first guy, we've got analytic. We're looking at our limit as x approaches -3 of x plus 3 divided by x squared minus 9. So if we do direct substitution, I'll have -3 plus 3 divided by -3 squared minus 9, which is 0 divided by 0. It's undefined, and when we get that for a limit, we call it indeterminate. So that's no good. We have to keep going and try to simplify that. So we can simplify this one by factoring, because we know that x squared minus 9 is the difference of squares. So we can have x plus 3 divided by x plus 3 times x minus 3. You'll notice we have a common factor of x plus 3, so we tell that guy to get out of town. Then we're looking at the limit as x approaches -3 of 1 over x minus 3. Direct substitution into our simplified equation, -3 minus 3 gives us -1/6. All right. Next up is direct substitution. Numerical, which is where we substitute in a bunch of values to get our answer. So we look at both sides, because when we plug in -3, we get that undefined answer. So we're going to plug in -3.1 and then a value that's closer, -3.01, and do the same thing on the other side. Values that get closer and closer to that C that we're approaching. So I put up an example of using that -3.1, and that would give you -0.1639. For the other guys, you just substitute in, same process, and you'll get those values. So to find the limit overall, we have to look out from the left. So we're going towards -3. From the left, you put the little negative in there. So from the left, we're going in the table this way. It approaches -0.1664, right? And from the right, we're going the other direction. Well, I should say it approaches -1.66, repeating, because you'll notice we had 0.16 for the first one, 0.166 for the next one. So it's the same pattern on the left here. Since those are equal, we say our limit overall for -3 f of x is equal to -0.166 repeating or -1/6.